I'm Isaac.
Hello, my name is Cameron Williams.
I'm Jermaine Chambers, and we'll be learning about magnetism.
Alright, now to get started, we ask ourselves, what is magnetism?
Magnetism. It's when you have that nice little trinket that you got on vacation and you want to throw it on the fridge and give it to somebody as a gift, how it just comes together like that. And wow, how's that happen? Magnetism.
What is magnetism?
Magnetism. I guess magnetism is kind of like when stuff sticks together like glue, but it's not sticky, so I don't know. I guess magnetism.
Those are some good answers, but here's the correct definition.
Magnetism, a physical phenomenon produced by the motion of electric charge, resulting in attractive and repulsive forces between objects.
Now that you know a little bit about magnetism, my colleagues will now explain how to solve a couple of problems.
A long straight wire has a 12.3 amperes current flowing in the positive X direction, as shown in the figure. Close to the wire is a square loop of copper wire that carries a 2.01 amperes current in the direction shown. The near side of the loop is D equals 38.1 centimeters away from the wire. The length of each side of the square is a 1.19 meters. Find the net force between the two current-carrying objects.
Alright, so we're trying to look for the force between two wires carrying the current. So from our diagram, we know that 2 and 4 cancel each other out. And so we're just trying to look for 1 and 3. And our initial equation for force on a wire is F is equal to U naught times I1 times I2 times L, which is length over 2 pi times the distance between the wires. And from that, we got F1, or the force on wire 1 is equal to U naught times IW times I1 times distance A over 2 pi times D plus A, which is the distance of this whole thing. And for the force on 3, we got U naught times IW times I1 times the distance A over 2 pi times D, or distance. So now I'll move over here, and now we can add both F1 and F3 to get our net force. And so, as you can see, we got U naught times IW times I1 times distance A over 2 pi, and we multiply that by 1 times D minus 1 over D plus A. And now we plug in. And so for U naught, we got 4 pi times 10 to the negative 7. And for IW, we had 17.3 amps. For I1, we had 2.01 amps. For distance A, we had 1.19 meters. And we divide that by 2 pi. And then we multiply that by 1 over 38.1 times 10 to the negative 2 meters, since 0.381 is centimeters. And we do the same thing here, but we add 1.19 since it's A. And once you put that into your calculator, your answer is going to be 117 times 10 to the negative 7 newtons. And that is your net force between two wires carrying the current.
Good job, Mr. Chambers. I could not have said it better myself. We will take a break with another fun fact.
Magnetic compasses use the Earth's magnetic field to help navigate in north, south, east, and west directions.
Thank you for waiting patiently throughout the break. Now we will have Isaac explain magnetism and its direction.
On the diagram, draw the likely path of a proton traveling at the same speed in an identical field. The right-hand rule describes the force exerted by a magnetic field, B, on a particle with a positive charge Q moving with a velocity V. To find the direction of the magnetic force, point your thumb in the direction of the velocity of the moving charged particle, and your index finger in the direction of the magnetic field, and your middle finger then gives you the direction of the magnetic force. It's also easy to remember that the direction of the force is always perpendicular to both the velocity of the moving charged particle and the magnetic field. If we look at the problem, we can now assume that the proton's direction, which is perpendicular to the magnetic field, B.
Great job, Isaac, or should I say, Sir Isaac Newton. Now that you have a better understanding of magnetism and its direction, we will move on to solenoids, but first, let's take a break.
Did you know that there are 5 planets in our solar system that have magnetic fields? They include Earth, Saturn, Jupiter, Neptune, and Uranus.
Right. Once again, thank you for waiting patiently during the break. Now we will have Cameron explain how to solve a problem dealing with the solenoids.
A current of 2.13 amperes is flowing through a 956 turn solenoid of length L equals 43.1 centimeters. What is the magnitude of the magnetic field inside the solenoid?
Alright, so the problem states the solenoid has a current of 2.13 amps. It turns 956 times and has a length of 0.43 meters. So what I'm trying to find is the number of turns it makes per meter, and I'm trying to find the magnitude of the magnetic field in the solenoid. And so for the first part, you start with this equation. You plug in the number of turns and the length, which is 956 turns and 0.43 meters. Plug that in and you get 2,218.094 turns per meter. And for the magnitude of the magnetic field in the solenoid, you use this equation, mu naught, which is a constant. You plug in your number of turns per meter, which is 2,218.904 times the length of the solenoid. And when you plug that in, you get 5.94 times 10 to the negative 3. Thank you, Cameron, for explaining solenoids. Today we learned the true meaning of magnetism and how to solve problems dealing with it. I hope you learned something from this video, and I would like to say good night, PV, and good night, America.